Hello. In the previous lecture, we were doing limits on continuity. Today, we are going to continue with the same theme. But today, additionally, we are also going to see how differentiability works in the case of complex analysis. So without wasting time, let us start with the discussion on continuity and differentiability today. We've already had done continuity in detail. A few things needs to be done with that I'll do today. And a few more things like uniform continuity, I'm skipping for now. We'll see it on the later date. Okay. Because an important topic called as Cauchy-Riemann condition would follow. So therefore, I'll concentrate more on analytic functions and Cauchy-Riemann conditions after this. So we have already know what is continuity. One important point regards continuity is the open set characterization. Open set characterization of continuous functions. And what it is? See, I'm just giving you let f be defined from D to C be a function. And then f is continuous on D if and only if for every open set O contained in C, F inverse O is also open. What is F inverse O? F inverse O will contain Z belongs to D such that Fz belongs to is open in D. So what does it mean? It means that if O is open set in C, then F inverse O is also open. Okay. So this is an important topic. It is all I have written it. I have introduced this particular topic as open set characterization of continuous functions. So a little bit of a sketch of proof I'm going to give so that you're able to understand what I want to convey. A little proof. Since it is if and only if conditions, we'll first work backwards. Let us try to work backwards. That is, let us assume that f if O is open set, if O is open set, and then let us also assume that f inverse O is open. So suppose for each open set, open set O contained in C, f inverse O is open. Now, I'll prove that if this is the case, then fx must be continuous because see here condition is if and only if now. So I have to do both sides now. So I'll assume first that my for open set O, f inverse O is open, and now I will prove that taking this, I'll prove that f is continuous on D. Okay, so our f is continuous at some point. Okay, f is continuous at some point. F is continuous. Okay, so this is what I'm going to prove. So suppose for each open set O belongs to C, F inverse O is open. So what does open set means? If a set is open, let's say if set is open, then if I take any point Z dot would be an interior point. It implies that the neighborhood containing Z naught, there must be some neighborhood containing Z naught that must be contained in the set itself. So if I'm claiming that my set S is open, then I take any element Z naught from S, and then there should be some neighborhood enclosing Z naught, which must be contained in S. Then I'll say that my set S is an open set. So if I'm saying that F inverse O is open, so let me consider an open set. So let me consider an open set. I know that Z naught belongs to D. if Z naught belongs to D, and let me take an open set, an open disk centered at FZ naught and radius epsilon. So what is FZ naught? If Z naught belongs to D, so let's say this is your Z plane and this is your W plane. Okay. So the image of Z naught under the transformation F in W, here it is FZ naught. So I'm considering this is basically C and this is basically a subset in D. Okay, so what I'll do, I'm considering an open set or open disk centered at FZ naught with radius epsilon. You know that open disk is an open set. So this is open in C. We know that this is open in C. And if it is open in C, then by hypothesis, let's say, let us name it as A. Then by hypothesis, we know that F inverse A must be open in D, right? So by hypothesis, we know that F inverse A must be open in D. Now, since F inverse A is open in D, and we know that what is FZ naught? FZ naught is the image of point Z naught. So it implies that F inverse A must be open in D, and we already know that Z naught belongs to F inverse A. So if Z naught belongs to F inverse A, then some neighborhood containing Z naught must also be contained in F inverse A. So it implies what? It implies that there must be some neighborhood centered at Z naught such that it must be contained in F inverse A. Basically, if I'm saying that Z naught is an element in F inverse A, then and F inverse A is open, that then any neighborhood, there must be some neighborhood uh, around Z naught which must be contained in F inverse A. So what does it mean? If you really think, what does it, if you really do some, if I just again take inverse, so it implies that image of F for all these Z, what these Z are? These Zs contain all those Z which are at a distance from Z naught. Sorry, all these Z are what? These Zs will be from this particular region, that is mod of Z minus Z naught less than 10. And they must be contained in A, and I already know what is A. A is my uh, open disk centered at FZ naught and radius epsilon. So what does it mean? In other words, it means, so if I want to write in other words, it means that FZ is contained in FZ naught, open disk FZ naught, comma epsilon, that is FZ minus FZ naught modulus can be made less than epsilon when we are taking these Z, whenever whenever Z minus Z naught mod is less than that. And the obviously we are talking of domain. So basically we are talking of domain D. So basically we are taking these Z such that Z minus Z naught mod is less than 10, and where these Z are coming from this domain D. So what do you think this definition? It implies what? It implies that F is a continuous function on D. No, not D, sorry, right now Z naught. And since Z naught is an arbitrary point, you can do it for all the points in D. So this is one point. So here we have established the continuity on Z naught. Now next, let us take another way. Let us assume that now function is continuous. Now let us assume that F is continuous on D, and let O be an open set. O be an open set. Now here we'll prove that F inverse A is F inverse O is open. So we have to prove we have to prove that F inverse O is open. Okay, so F is continuous on D and O be an open set in C. If F inverse O is phi, then nothing to prove because it is an open set. So is open. So I'm not proving in this case, but if F inverse O is not phi, sorry, if F inverse O is not equal to phi, then there must be some element that says Z naught belongs to D such that F Z naught belongs to O. Now we know that O is open. What does it mean? Since O is open, it implies that there must be some open disk containing Fz naught, which must be contained in O. Okay, so if O is an open set, then an Fz naught is what? Fz naught is contained in O. So Fz naught is an interior point. So there must be some neighborhood of Fz naught which must be contained in O. Okay. We already know that F is continuous. So what continuity implies? Continuity condition implies that Fz belongs to this open disk, or I will write Fz minus Fz naught mod is less than epsilon whenever Z minus Z naught mod is less than del or delta Z naught comma del. That is, Z is contained in this open disk centered at Z naught and radius del. So what does it imply? It implies that if Fz is contained in this, when if Fz is contained in this particular open disk centered at Fz naught comma epsilon, when Z is contained in Z naught comma del. So uh, it implies that this disk is contained in F inverse. Okay, so from the inverse, from the definition of the inverse, we know that we can clearly know from here itself that Z belongs to F inverse. So what does it mean? It means that whenever your function is such that Fz minus Fz naught is less than del epsilon, then Z minus Z naught mod is less than del. And where it is contained in F inverse. So basically I'm writing that an open disk centered at Z naught is contained in F inverse O. And we already know that Z naught is contained is an element of F inverse O. So it implies that if Z naught is contained is contained in F inverse O, then an open disk centered at Z naught is also contained in F inverse O. It implies that F inverse O is open in D. So I hope I have conveyed my idea. You have to see all the more elaborate proof in the books. So this is a little bit of proof for this. I have this particular theorem, and theorem is very important. Similar things you might have done in your real analysis also. This is set again. I'm revising. This is said as this. This I'm calling as open set characterization of continuous function. Let f be defined from D to C be a function. Then f is continuous on D if and only if for every open set O contained in C, f inverse O is also open in D. So basically, if you're taking an open set in C, and if you want to find the pre-image or inverse image, then that inverse image is also open. So this is one very important theorem that you should keep in mind before we are going to sum up this continuous functions. Another thing is the preserving that continuous function preserves the connectedness. This is another important thing. I hope you are aware of the definition for connectedness. if you're not aware that when the set is said to be connected or disconnected, I would urge you to see that particular lecture on connected and disconnected set. And how to write what is connected and disconnected so that you get to know. So a set S contained in C is said to be disconnected. Is said to be disconnected or separated if there exist two non-empty disjoint if there exist two non-empty disjoint open sets A and B such that S is contained in A union B and S intersection A is phi and S intersection sorry it's not phi sorry and S intersection B is also not phi. And you know that A and B are disjoint, so A intersection B is phi. And if these conditions don't comply, then the set is connected. If S is not disconnected, then it implies that S is connected. Okay, so this is the definition. Now let us move to what I want to convey in this lecture. So, okay. So one very important thing that I want to convey is that if F is defined from D to C, if F is defined from D to C, and let it be a continuous function. Let F be defined from D to C be a continuous function. And we are assuming that D be a connected set. D be a connected set. Then the image of D under this transformation F or under this function F is also connected. Then FD is connected. So this is an important theorem. That is what you can say. That is a continuity. It preserves the connectedness. So basically, if F is a continuous function from D to C, and D is a connected set, then the image of F over D is also connected. So this is an important thing that you have to keep in mind. So therefore, this is an important theorem. So therefore, I have written it here. Let's say how to go about the proof. Suppose this is not true. Suppose this is not true. So we'll go with the contradiction. Suppose this is not true. In that particular scenario, what will happen? There would be two non-empty disjoint subsets of what FD. So if this is not true, that is if FD is not connected, then there must exist two non-empty open. These are non-empty open subsets. Okay, these are non-empty open subsets such that I can write my FD as union of both of them. And I know that V1 intersection V2, this is equals to what? This is phi. This I know already. Okay. Now we know that if FD is not connected, then it must be expressed as union of two non-empty open subsets, which is V1 and V2. And by theorem, we know that already we know that it implies that what? And let's say, and we already know that if V1 is open, if V1 is open, then F inverse V1 must be open if F is continuous. So I'll write that F inverse V1 must be equal to some open set. Let us say I'm writing it as U1, and F inverse V2 is equal to some U2. U2. Okay. Here U1 and these both are U1 and U2 are both non-empty open subsets of D. This is from the above theorem. So if we know that V1 is an open, V1 is a open subset of set, V2 is open subset, then we know that F inverse V1 must be equals to some other open set. That is, let's say U1, F inverse V2 is another open set, let's say U2. And what is this? We know that V1 and V2 are V1 and V2 are what? V1 and V2 are what you can say. V1 and V2 are non-empty disjoint sets. So we know that these U1 and U2 are disjoint, and we know that the entire D can be made out of this U1 and U2. So it implies what? It implies that D is also disconnected. It means that D is disconnected, right? From here it is clear, because how can I express my D? So if V1 is open, then F inverse V1 is equals to U1, which is open. F inverse V2 is what? U2, which is again open. So from the definition, we know that U1 intersection U2 is phi, and U1 union U2 will comprise the entire D. It implies D is disconnected, which again brings the contradiction, because we know that D is connected. So this is a contradiction to the fact that D is disconnected. So therefore, this cannot be the truth. That is, FD must be a connected set. So I've given you a little bit of understanding of this thing. You can do it on your own. I'll urge you to find textbooks where this proof is given in more elaborate way. So always remember that if F is defined from D to C and it is a continuous function, and let's say D is a connected set, then the image of F uh, is also connected. That is the range. If D is connected, then the image of D is also connected under the function F. So basically what it means that my continuity preserves the connectedness. So this is important point that you should remember, that the continuity preserves connectedness. I hope it is clear. So this sums up our lectures on continuity. However, there are still few topics which are left. We'll see all those topics later on. But now let us first introduce the notion of differentiability. First thing you have to keep in mind that since whenever we study complex analysis, we know that basically it is a isomorphic structure to R square. So most of the rules, we know that C is nothing but, we know that this particular algebraic structure, or if you continue this, these are one and the same thing. Either you identify any point in the complex plane, or you identify that point as an ordered pair in Cartesian plane. These are one and the same thing. So most of the concepts that we have discussed in R square will directly get transferred here. Okay, this is something that you have to keep in mind. Okay, so this is first thing. So most of the concepts would remain the same. So the definitions, most of the formulas that you have discussed will remain the same. So I'm writing here. So formulas concerning the differentiation remains the same. And we know that in R square also, limit is defined only if it is uh, path independent. Continuity condition also requires the path independentness. That is, if you want to say that my function is continuous at z naught, then limit f z at z tends to z naught must be equal to f z naught, and this should be unique. It cannot be the case that if you take some different path, then it is coming some different limit. If you're taking some different path, then the limit is coming different. So in any way, this limit should be path independent. This is something that we also do in the calculus or multivariable calculus. So all these concepts are going to remain the same. The formulas concerning differentiation, that is, if I say what would be the derivative of e raised to power z, so it will remain e raised to power z. What is the derivative of sine z? It will remain cos z. So the formulas concerning the derivative would remain same. The important thing that you should understand is the definition, and that is also precisely the same that we write in the real analysis. But let us start with the definition. So let us say that if a function is defined from D to C and it is differentiable, and here is, I think D is a non-empty subset of C only. So if f is defined from D to C and if it is differentiable at some point z naught belongs to D, then f z naught plus h minus f z naught divided by h. This limit h tends to 0 must exist, and it should be path independent also. Must exist, and we denote this is equivalent to at equivalent to f dash z. We say that the function is completely differentiable on D if it is differentiable at each point on D. So we say that f is said to be differentiable f is said to be differentiable on D if it is differentiable at each point on D. This is an important way of writing the differentiability condition. Okay, so this is how you write the differentiability condition. As we are aware, we can you can find some books which will write some different definition. Let's say, uh, most formally, I know that if I am writing this, another way of writing this can be fz minus fz naught upon h minus f dash z naught. This whole mod can be made less than epsilon. Can be made less than epsilon whenever we know that z minus z naught is less than del, and let us take a puncture disk. We'll see how things goes. This is how it is. So basically, we are now defining a new function that is eta z. It is nothing but it is equals to what? Is equals to fz minus fz naught divided by h, or simply you can write this as h as z minus z naught only. Okay, so I'll write it as z minus z naught. Okay, minus f dash z naught, this whole mod is less than epsilon whenever z minus z naught is less than 10 and greater than 0. That is, if z lies in the punctured disk uh, centered at z naught and radius 10. So basically, I'll write if and 0 otherwise. So I'll write 0 otherwise. That is, if z is equal to z naught, then it is equal to 0. Okay. So we have defined some other function eta z. We have defined some different function eta z, and this function we have defined in a way that it becomes, if f is differentiable, then this particular limit as z tends to z naught would be nothing but f dash z naught. So f dash z naught minus f dash z naught must be 0. So I have defined eta z to be a continuous function. So here eta z is a continuous function such that limit z tends to z naught, eta z is equals to 0, and which is nothing but it is equals to eta z naught. So I've defined a function eta z, uh, keeping in mind that my function fz is differentiable. So this is one thing. So we can rewrite our condition, that is, what was eta z from the definition of eta z, I can write that fz is equals to what? It is equals to fz naught plus z minus z naught, f dash z naught, and then plus z minus z naught eta z. So from the definition of eta z itself, you can do this thing. I mean, you can do this thing from here. You can take this z minus z naught here. It will multiply here. Again, take there. So fz is equal to this. So another way of defining differentiability condition is that the function can be expressed as fz naught plus z minus z naught f dash z naught plus z minus z naught into some continuous function, where continuous function eta z is defined this way. Okay, so this is some, like, you can write this way also. Okay, so if I want to say the same thing, we can write that if f is defined from D to C, if f is defined from D to C, then f is differentiable if and only if f is differentiable if and only if or at z naught. Or I can write that f dash z naught exist, f dash z naught f dash z naught exist if and only if there exists a function zeta from D to C, sorry, eta from D to C, such that eta is continuous at z naught. So this is what we have written above. Okay. So this is another way of writing conditional differentiability. However, I'm not going to use these things quite much. I'm going to use this particular definition. That is, if f is said to be differentiable on D, if it is differentiable at each point on D, and how to say that it is differentiable at point z naught, if limit h tends to 0, f of z naught plus h minus f z naught upon h exists. If this particular limit exists, then I'll say that my function is differentiable at z naught. Another way of writing it would be fz minus fz naught divided by z minus z naught, limit z tends to z naught. So this is how you take the definition of, write the definition of differentiability. Okay, I hope it is clear. Okay, another way of writing the same definition for differentiability would be that f is differentiable at z naught. We know that if it is differentiable at z naught, then limit z tends to z naught, fz minus fz naught upon z minus z naught, and this should exist, and this should be equal to what? F dash z naught. We know this already. So if f is differentiable at z naught, this is the case. Or if I want to write in another fashion, I will write that fz, I can write fz as equals to fz naught plus z minus z naught f dash z naught. And if I add some linear function to it, let's say some ez, then one has to remember that this ez upon z minus z naught must, and if I take a limit z tends to z naught, then this must go towards 0. Why? Because if it doesn't go towards 0, then it will violate the definition for the differentiability. Because see, function is differentiable only if f dash z naught can be written as what? Fz minus fz naught upon z minus z naught in the condition limit z tends to z naught. So if it so happens that it is non-zero, then it will violate the definition for the differentiability. So if function is differentiable at z naught, if and only if fz can be written as fz naught plus z minus z naught f dash z plus some ez, where limit z tends to z naught, ez upon z minus z naught must be equal to 0. This is how you define another way of differentiability. But keep in mind, we are going to just use this definition. That is, if function is differentiable at z naught, then limit z tends to z naught, fz minus fz naught upon z minus z naught, this limit must exist. Then we'll say that this is equal to what? F dash z naught. So all those discussions that I've done, these are all bookish discussions. You can avoid them, but you can keep things in mind. At times in examination, you may find that such definitions are coming and then you will be confused. So therefore, I have given these definitions to you. Okay. Don't worry about these definitions. Okay. So this is one thing. Now, another important point that you should write here itself, that a real valued function, a real valued function of a complex variable. So I'm saying that the domain is complex, but the output, that is, the output is real. So a real valued function of a complex variable, a real valued function of a complex variable either has a zero derivative zero derivative or does not have. Okay. So either it has a zero derivative or it does not have. So basically, how do I prove? If it does not have, then it's fine. That is, if it is non-differentiable, that it may not have a derivative. But what about this zero derivative? So let me take that fz be a real valued function. Let fz be a let fz be a real valued function. Let fz be a real valued function. Now, let us say that it is differentiable at point A. Let us say that it is differentiable at some point A. Okay, then it implies what? It implies that f of A plus h minus f of A divided by h limit h tends to 0. It must be some limit, and it should be some number, let's say f dash A, and it should exist Okay, if f is differentiable at a, then f a plus h minus f a upon h tends to 0, it should be equal to what? F dash a. Now, if you take two paths, let me take two paths. If I am on the real axis, and if I take h tends to 0 on the real axis, okay, then my f dash a must be real, because see, this is already real, this is already real. So real minus real is real, but h, if I'm uh, constraining my h along the real axis such that h tends to 0, then I can say that my f dash a must be real. Okay. And if I constrain my h in this direction, that is the imaginary axis, and h tends to 0, that is, if h tends to 0 along the imaginary axis, then f dash a would be imaginary. Because see, f is already real, f of a plus h is real, f of a is real, so real minus real is real, but h is tending to 0 along the imaginary line. So f dash a is then imaginary. If I'm saying that my f dash a exists, then it cannot be possible that f dash a becomes real if I take one part and f dash a becomes purely imaginary if I take another part. So only way that they can be equal is that f dash a becomes what? 0. So always remember, if f is a real valued function of a complex variable, then its derivative would either exist or does not exist. If the derivative exists, then the value of the derivative would be 0. So this is what we have written here. Okay, so this is was one theorem that I have already placed in front of you. Now, let us come to an important point. If this is something that you know from your childhood also, like calculus times also, that if f has a derivative, if f has a derivative at z naught, then it is continuous at z naught. Then it implies that f is continuous at z naught. So if f has a derivative at z naught, then f is continuous at z naught. However, we know that continuity of f at z naught does not imply differentiability of f. So converse not true, not always true. So converse not always true. Okay, so converse is not always true. So if f is continuous at z naught, it does not necessarily imply that f is differentiable at z naught. One of the example is, you know that in your calculus, you do fx is equal to modulus of x. So you know that f is continuous at 0, modulus of x is continuous at 0, but it is not differentiable at 0. However, we cannot make the graph of these functions. Okay, so basically these are not kind of graphs. And also you should not associate, this is something that again, okay, this was important thing. Uh, Actually, what happens when we write that f dash x, what does it represent? If I am having a graph, let's say this, of fx, then f dash x represents the, at point, let's say x naught, represents the slope of the tangent drawn at that particular point. So the derivative at any point represents the slope of the tangent drawn at that particular point. This is the geometrical meaning. However, f dash z does not have any such geometrical meaning. F dash z does not have the above geometrical meaning. Because you have to understand, okay, about geometrical meaning. Because, you know, if z you cannot make on like like on the plane, because see, Z contains two variables, no? Z contains two things like X and Y. So basically, I'm not talking of two variable calculus. Two variable calculus, you cannot plot it on a plane basically. So if you're doing Y is equal to Fx, then it's fine. Then it's fine. But this does not apply here. So you have to remember that you cannot visualize your F dash Z as a slope of tangent drawn at some point. Let's say here F dash X at X naught implies what? It implies a slope of tangent drawn at point X naught. So this is the geometrical meaning. However, this geometrical meaning does not apply for the its complex analog. That is, if I'm discussing the derivative of function, derivative of a complex valued function, then F dash Z does not imply slope of some curve. Okay, so this is something that you have to remember. Okay, at times you may be asked in the exam, so you have to remember this. Okay, now let's say F mod Z. However, I have just given the graph of modulus of X, and I have explained that in real analysis, we take this example that this particular modulus of X is continuous at X equal to 0, but it is not differentiable. So differentiability of function at Z naught implies continuity of function at Z naught, but continuity of function at Z naught does not imply differentiability at Z naught. Here also we are taking the function as modulus of X only. And let us say that your H is some H1 plus iota H2. Here H1 and H2 are both real. H1 and H2 are both real. Okay. Now, let us try to find the differentiability at 0. So it will be like F(H)(0) plus H minus F(0) divided by H. So we want to find this limit. Limit H tends to 0. And this will be equals to what? It will be equals to modulus of H divided by H. And we know that this can take all different values. Let's say now, if I take H to be purely real, if I take H to be purely real, then this will be equals to 1. If I take H to be purely uh, real, and let's say H1 is positive, then it will be what? Then it will be 1. And if I take again purely real, but H1 to be negative, then this would be -1. If I take H to be equals to purely imaginary, and here H2, whatever I'm finding, H2 is positive, and obviously H2 should go towards tends to 0 also. So I'm writing H2 should tend to 0. And similarly, in both of these cases, I'm writing that H1 is very small, that is H1 tends to 0. If this is the case, then it will give me a value of iota. Sorry, minus iota. Okay, because, so sorry, minus iota. Okay, I'm leaving up to you to visualize this. I think this is easy to calculate. Okay, so if H2 is positive, then H2 mod upon H2. H2 mod would be like H mod is what? Iota H2 mod and divided by iota H2. So this will be minus iota here. And if you take H to be equals to 0 plus iota H2 in a way that H2 is less than 0. Okay, and H2 is also tending to 0. So this will give me positive iota, simply positive. Okay, so all these things, so clearly I know that modulus of Z is not differentiable at Z equal to 0. Okay. However, in real analysis, we have seen that modulus of X is differentiable for all other points except 0. In complex analysis version, it would be interesting to note that Z, modulus of Z is nowhere differentiable. So this is all the more bigger thing that I'm writing here. Modulus of Z is nowhere differentiable. this is something I'm leaving up to you as an exercise. Try to do it. If you're not able to do, then we'll do it in the later class. So what I wanted to convey that in real analysis, if you are considering modulus of x, so modulus of x is non-differentiable only at a point, otherwise it is differentiable. The slope here is 1, the slope here is minus 1. However, in complex analysis, mod z is not differentiable at z equal to 0, fine, but mod z is non-differentiable on entire C, but continuous in C. So this I'm leaving up to you, that you would find that whether how to prove that mod z is nowhere differentiable in C. So you have to take any point z not belongs to C and do the same thing that I did above and then try to reciprocate. So in the next class, we are going to do a few more topics of differentiability, and then we'll try to move uh, on to something called as the Cauchy-Riemann conditions. I hope you are getting benefited by these lectures. Kindly let me know if there are some doubts and difficulties in the comment section, and kindly let me know if there's certain things that I can improve upon. Till then, take care. Bye-bye.